Okay, next we're going to look at problem number 10. Problem number 10 is kind of like two problems in one. So in the first situation, we're going to fire something with an initial velocity of 15 meters per second upward at a 35-degree angle. And that's going to be like a traditional problem of firing something off a cliff. But we're going to add on some extra questions, such as how long is it in the air, how far over does it land, and what is the final velocity when it hits the ground. So again, we're going to be looking for the time it's in the air, how far over does it land, and the final velocity that it hits the ground. And then we're going to do a second problem where we are going to fire it downward with the same initial velocity of 15 and at a 35-degree angle. And again, how long is this one in the air? How far over does it land? And what is the final velocity that it hits the ground? So I'm going to do the first, or what is labeled number 2. I'm going to do the traditional problem first, because we're going to need to extract some information out of this problem in order to solve the second problem. Alright, so I'm going to start by drawing my own cliff over here so that I can label some things on my picture a little bit better. And we're going to fire it at an angle so that it comes down something like this. Alright, in the problem it tells us that the height of the cliff is 100 meters. And we're firing it with initial velocity of 15 at a 35-degree angle. So just like normal, I'm going to find my x and y components. If you watched some of the previous videos, you might have noticed that I did not write down the x component because I didn't need it. But in this problem, I know that I do need it. So that's going to be 15 cosine 35, and that equals 12.29. And then the y component, Vy, is going to be 15 sine 35, and that equals 8.6. So I'm going to use the y direction to figure out how long it takes to go to the top here. So at the top in the y direction would have a final velocity of 0. The acceleration is going to be negative 9.8, and I'm using that to find time. So let's use our first acceleration equation. So Vf equals Vi plus At. But again, this is in the y direction. So this is a 0, 8.6, minus 9.8 because it's slowing down, and I'm solving for t. Alright, so the time turns out to be 8.78 seconds. So I'm going to write down a little up here. You can circle that. Alright, so that's the time it takes to go up to the top here. Alright, the other thing that I need to know is how high up it's going to travel. And so I'm just going to throw a little d in my list over here. And like before, we can use our third acceleration equation. So Vf squared equals Vi squared plus 2AD. So this is going to be a 0, 8.6 squared. The negative actually comes from the 9.8 and D. And we find out that it goes 3.77 meters higher than the cliff. Alright, so this is 3.77 meters. And the height of the cliff is 100. So now I'm going to go over here to the other side. And we can figure out how long it would take the object to hit the ground. We can pretend we just dropped it from the very top, and that would be the same amount of time as it would take to parabola down. So I'm going to write down VIT plus 1/2 AT squared. And because I'm pretending I'm dropping it in the y direction, that's 0. So the D is going to be 100 plus 3.77, so that's 103.77 plus 1/2, 9.8 times t squared. So the time it takes to go down is going to be 4.6 seconds. So we'll circle that. But we need to know the total time that it's in the air. So I'm going to have to take the up time and the down time and add that together, and that would give me my total time. And so I'm actually going to write the total time over here. So when I add those two things together, it adds up to 5.48 seconds. So we'll store that. All right, the next question on my list is how far over it goes. So I'm going to solve that down here where I have a little bit more space. In the x direction, it's constant velocity because we know those x arrows do not change. And so the x velocity is 12.29. 12.29. I'm looking for dx. And it is in the air for a total amount of time of 5.48 seconds, which means that it has enough time to travel 67.35 meters. So I'm going to circle that, and I'm going to write that in my chart over here. So 67.35 meters. All right, the last question is, with what velocity does it hit the ground? So I'm going to come over here. So when the object hits the ground, it is going to hit the ground with an x component that doesn't change because the x arrows always stay the same. So we already know that number. Vx is going to be 12.29. But we need to figure out what the y arrow is. And to figure out the y arrow, it really is this equation. Vf equals Vi plus At in the y direction. But this y arrow is like pretending we're dropping it from the top of the cliff, and then this would become a 0. So to get the Vy arrow, it ends up turning out to be 9.8 times however long it's falling. So 9.8, and it is falling right up here for a time of 4.6 seconds. 4.6 seconds. So if I multiply that together, 9.8 times 4.6, I get 45.08. So that's the velocity in the y direction. This is the velocity in the x direction. So to find the velocity with which it hits the ground, then I'm going to have to parallelogram method those. Let's call this the resultant velocity. And so a little a squared plus b squared, and we find out that the resultant velocity is 46.73 meters per second. And you'll also notice that it really is hitting the ground with an angle here, And so I could use a little tangent here to find that angle with which it hits the ground, and that would be 45.08 over 12.29. Theta equals, let's do that real quick. So we have 45.08 divided by 12.29, inverse tan of the answer. And I get 74.75 degrees. We'll call that south of east. All right, so we can copy that onto our board over here. And so this is 46.73 meters per second at a 74.75 degrees of south of east. Okay, so the point that I want to make right now is that really, if I cover up this bottom piece here, let me do it with something clear. If I cover this up, this right here is really a symmetrical problem. So I fired this with a velocity of 15, and it has an x component and it has a y component. And if I added that x and the y component together, I would obviously get the 15. So when it hits the ground, the x component is going to stay the same. The y component, the y arrow is going to get shorter and shorter and eventually go away, and then get longer and longer and longer. And the y arrow over here, I'll call it Vy, will end up being the exact same Vy arrow over here, because the top part of the problem is a symmetrical problem. So why that's important is if I then cover this part up, this here and this here are also identical paths. Identical paths. And what that means is the time could be different because of the asymmetry, or that this part was symmetrical. This one had to go up and then come down. This one only has to come down. dx, I can see that the dx for this one is much shorter than the dx of this one. But interestingly, the final velocity of these two things should turn out to be the same because these paths are the same. So we want to see if that happens when we do the second piece of the problem. All right, so we're going to move this aside. We're going to label this one 10A. And now we're going to do the second part of 10A over here. So the second part of 10A is that we're going to have our cliff that's going to look like this. I got to get the right notes over here. All right, so we're going to have our cliff. We'll make it look like this. And we are going to fire downward at an angle like this. So our angle is still 35 degrees. And the velocity that we're firing it downward is going to still be 15. So what that means is that we still have an x component, and my x component is going to be 15 cosine of 35, just like before. So we know that that is 12.29. We're going to have a y component. That's going to be 15 sine of 35, just like before. So that's going to be 8.6. All right, this is not a perfect parabola, but if I pretend that I dropped it over here, I would still have an acceleration of 9.8. I really don't know how long it's going to be in the air, and I really would like to know what the final velocity is in the y direction. So I'm just going to leave that there for a minute. So I do know what the x velocity is because it never changes. So that's going to be 12.29. So I'm trying to figure out this over here. I'm trying to figure out the y component. To find the y component, I am going to have to figure out what this time is here. And I'll be honest, I'm watching my computer clock right now to see if this thing is going to close out on me in about 30 seconds. Okay, so to figure out the time, so we know that the total time to go up, down, and fall is 5.48 seconds. So I'm going to go backwards here for a minute. I know that the time to go up is 0.878. So this time to go down to the symmetrical part would be another 0.878. So I'm trying to figure out what this time is right here. So to do that, I'm going to take the 5.48 seconds, which is the total time, 5.48 seconds. And I'm going to subtract the time to go up, 0.878. And then I'm going to subtract the time to go down just to the symmetrical part, 0.878. And then I get 3.724 seconds. That means that this little piece here is a time of 3.724 seconds. So I'm going to copy that on here. So this little piece is 3.724 seconds. I need that because now I can find the final velocity in the y direction. I'm going to write down y. So the final velocity in the y direction is going to be equal to this 8.6 because I'm firing it downward with that y component, plus 9.8 because it's going to be speeding up as it's falling, and it's going to be in the air for 3.724 seconds. So the y component is going to turn out to be approximately 45 meters per second. And why I care about that is I can copy that over here then. And now I can do the same thing that I did before. But I want to point out that our answers here are the same. 12.29, this is 45, this was 45.08. We'll just call that round off error. So we're getting the exact same resultant velocity. We're getting 46.73, and when I do tangent, I'm going to get that same angle of 74.75 degrees south of east. So I can write that back on my chart over here. The time that this one is in the air is 3.724 seconds. The final velocity is going to be the same, 74.75 south of east. And now I just got to find dx. All right, so Vx equals dx over time. And Vx is 12.29. And it's in the air for this 3-some seconds. And we find out that it has enough time to travel over 45.77 meters. So we'll copy that down. 45.77 meters. So I think that these are the answers for 7A. And I'll be honest, I have no intention of doing this problem in variables. And you don't have to do that either. That was kind of just for fun and for a challenge.